today. The first is Ahmed Sanaullah, who is going to give the first of 3 talks about paper reading. And so I'm happy to see that we have several new members presumably coming for that. And then our second talk today is going to be by Cagri Yoruk, who is going to give us an update on his work in the ChRIS project, which is an active project that's been going on between Boston Children's Hospital and Red Hat for quite a while now. And we also have at least one of his mentors here. So without further ado, I'll hand it over to Ahmed Sanaullah, and you can get started.
Thank you, Heidi. Let me just share my screen here. Let's see. Is it showing? I can't tell.
Yes, it is.
Awesome. All right, perfect. Thank you. So welcome everyone to the first pilot session for the research paper reading group. Just to give an overview, this is session 1 of 3. This particular session is going to talk about research papers in general, what they are, the different types, how do you find them, and what we're really going to try and emphasize on is the value of research papers, not just for the folks who have expertise in the specific technical field that the paper is written for, but for folks who are interested generally in finding out more about that area. Because of the content, this is going to be more presentation style, but the next couple of sessions are going to be more interactive. And even in this session, if you have any comments or suggestions or corrections or perspectives you want to share, please feel free to interrupt me and do that. I would love that. This is interactive as well. So that being said, let's start with this particular session, which is going to be kicked off with the question, what is a typical research paper? There's no formal definition for this. There's hundreds of ways you could define this. In my experience, most papers that I've come across in computer science and engineering can be put into 2 categories. One is an application paper. This is saying that you had an application, this was important, let's say identifying or detecting cancer. And then you saw that there was a problem or a limitation. Let's say it was taking too long or it was not as accurate as it should be. And then you proposed that using my new technique, which could be a new algorithm or a new technology that you're leveraging, you're able to solve that problem. And that's what the paper is going to do. It's going to document your novel technique. Then there's also systems papers, which have a broader context. This could be something like, I built a new compiler or a new operating system, and that's going to benefit a whole bunch of applications instead of one specific one. So different categories of papers, each with different targets. Now, based on where the project is in its cycle, there could be different papers that are getting written for it. Normally, projects start off with some research where you try to look at what's already out there, you do some initial findings, and they're good stuff, and there's important findings. There's just not enough, substantial enough to form a conference paper. So what you can do is you can write a workshop paper or a poster. And what that will do is, get your work out there and get you the recognition and the citations for the stuff that you've done. And once there's enough work, you can actually take that stuff, add on some new material, and combine 1 or 2 or more workshop papers or posters and write a conference paper. Those are basically talking about some very specific problems that have a few months of work put in to solve them. And then you can take 1 or more conference papers, as a rule of thumb, add on 30% new material, and you now have a journal paper, which is trying to solve this well-rounded problem. And the conference papers are like checkpoints towards reaching that goal. And then you take 1 or more journal papers, and that forms a PhD dissertation, which is sort of this high-level difficult problem in the specific field of research that you've done, that you've tackled, and that has advanced the field in a substantial way. And then based on that PhD dissertation, or one or more PhD dissertations, the professor and the students discovered, hold on, there's a whole bunch of stuff that needs to be done further. The problem has been solved, but that has led to a new set of problems being discovered. And we need to work on this now. And so you write a grant proposal. And if that gets funded, then a new set of projects start and this whole cycle begins again. So how do you find these papers? Everyone has their approach. This is typically mine, in that I use Google Scholar because it's a centralized resource finder. It allows me to look for papers across different places. They could be behind paywalls, as is the case with IEEE and ACM publications. Most of the time, not always. But there are also places where you can find them, publicly available, such as Archive, which is a place where you put preprints. Preprints are basically final versions of the PDFs of papers that the authors can upload. Because in a normal process, after getting a notification of acceptance, it takes a few months for that paper to be publicly available, even if it's on IEEE or ACM. But Archive gives you that platform where you can immediately start getting recognition and citations for your work, especially if it's a hot topic in the area. Then there are also browser extensions that will point you to where a free version of that paper is available somewhere on the internet. And then in some cases, such as if a professor has a National Science Foundation grant, the papers are also available on that professor's webpage or that lab's webpage. And one of the things that, I don't know how long this has been happening, but I've recently noticed is some of the highest tier conferences, the really prestigious places, they're actually making all the technical resources publicly available, such as the paper itself, recordings of the presentation, the slides, the source code artifacts. And that's amazing. That's really amazing stuff, because there is some high quality stuff that's being published here, and now it's accessible to everyone. Which sort of segues me into the next slide, which is, I use the word prestige. There is tiering that happens for conferences and journals. Different folks have different metrics that they use to rank certain conferences and journals over others. But usually the case is that when a conference has been, or a journal has been around long enough, more and more people want to submit to it. And given that there are, 20%, 25%, 17% acceptance rates, the quality of work that you need to get it through becomes more and more. The bar keeps getting raised year after year. And so it gets to a point where there are certain conferences, usually the newer ones, that you can do a month and a half's worth of work and publish there. And then there are conferences that require many years and many students' worth of work to get published, or many engineers' worth of work to get published. So for example, we had a couple of years back, we had a paper accepted at the Supercomputing Conference, which is one of the more prestigious conferences in our field. And that paper was about 4 or 5 students over 6-7 years worth of work in order to meet those requirements and get that through. So these tiers exist, but I emphasize that these are relative. Different folks will have different rankings for the different conferences in their field. And a rule of thumb that is generally employed is that higher tier conferences have high quality papers. It's not true. And that's because of the human element involved in this. There's no one central body that evaluates all papers out there. All papers that are submitted to research or to journals, submitted to conferences or journals, go through a peer review process. They are judged by your peers. If I'm submitting a paper to a conference, chances are that I will be reviewing some as well if I've signed up to be a reviewer. And the important thing here is that folks have different criteria with which they evaluate a certain field. They have differences in expertise. Some reviewers are more strict than others. Some have more expertise than others. Some have even actually worked directly on a problem, while others are just familiar with it. And as a result, you get this scenario where sometimes you have very high quality papers that get rejected and end up appearing in lower tier conferences, whereas you have some lesser quality papers that do get accepted at the highest tier conferences. So there's a whole variation in this. And so just going by this rule of thumb that if it is a higher tier location, then the papers must also be high quality is not always going to result in consistent quality papers. So rounding off this basic introduction, I want to talk a bit about typical paper formats. This can vary substantially. I cannot emphasize on this enough. This can vary a lot, but most papers that I've come across tend to follow something along the lines of this format, where there's the abstract, which is like the paper's elevator pitch. And then you get an introduction, which is going to give you an overview what the paper's about. And there are 5 major things that are talked about in the introduction. The first is what my professor used to call, and does call, motherhood and apple pie. This is basically trying to say something general about the field that most reviewers will and most readers will agree with. So for example, if I'm submitting an FPGA paper to an FPGA conference, I will say FPGAs are the best thing in the world. And most reviewers will agree with me. They will say, yep, that's true. But if I'm submitting an FPGA paper to a high-performance computing conference where there are GPU reviewers, they will not like that. I cannot say that. I have to say something more general. I have to say high-performance computing is really important, and we need to improve the compute performance, et cetera, et cetera. So this section is important, but it is also quite context-driven. Then we have, an outline of what the problem is that we try to solve. Then there is an overview that the authors provide of the solution that they are proposing. And then ideally, the authors explicitly list their contributions. And this is important. Contributions listed here are like terms of reference for the review, because what the authors are effectively saying here is, look, this problem exists, and we are claiming 2 things. We are claiming that by doing these contributions, this problem will be solved. These are valid contributions, and nobody has made them yet. And the second thing the authors are saying is, if we have made these contributions in our paper, then this paper should be considered an accept. And the stronger case we can build here, the stronger the accept should be. And then finally, we wrap up the introduction by just talking about the structure of the paper, just so that the reviewer knows what's coming. Because sometimes you're reading and you feel like, why haven't they talked about this yet? And this sort of tells you that the stuff that you're thinking about is coming, or it's not in the paper. And at this point, you can conclude safely that they have not talked about it. Then we get to the related work section. This is where the bulk of the research happened, because this is where with the authors, they say, we went back, we read papers, we looked at them, we studied them, we identified that, yes, this field is important, this topic is important, these problems exist, and there is nobody in prior art that's been able to solve it. And if we are able to do it, then we have made a substantial contribution. So the method section then talks about the design and implementation of the actual solution. Then this is followed by the results section, where you're saying, well, we built this system. Here is proof that this works. And normally you don't do exhaustive testing. That will take too many pages and too much time. You just have to show enough that the solution gets considered as plausible, at least, and just convinces the reviewers that, yes, you've done your design, it works, and it gives you the right expected result. At this point, most papers just wrap it up with the conclusion. Otherwise, you sometimes have this discussion session where you further analyze the solution and the results that you got, and really draw some interesting comparisons there. So, next we have what is the value of research, and this is what we have this paper rating group for. Is to really find value in this and show that there is value to be had in there in reading papers, and then reading papers as a group. And for me, there's actually a personal story here that I want to share. So this goes back to 2015 when I first came to the US to a PhD. And at that point, I was a hardware developer. My expertise was, analog circuits, power electronics, FPGA programming, and my advisor was doing high performance computing with FPGAs. He was building, multi FPGA systems, and so he gave me this book to read by Dali, and that's supposed to be one of the really great books in networks. And I did that. I read that. I read a few chapters, and I thought, I understand networks, I understand FPGAs, hence I should be able to do this no problem. My first week in, the professor has the entire lab sitting for a proposal writing session, and we're discussing ideas for a new grant that we're supposed to put together. And so what happens is it's just me and a couple of new PhD students and some experienced students and the professor. For 3 hours, I just sat and stared and stared. I had nothing to contribute, because while others were, exchanging ideas and really discussing the topic, none of it made any sense to me, not even the FPGA stuff. What had happened was that I had knowledge of hardware design, I had knowledge of topologies and advantages and disadvantages, but I had no practical knowledge of the field and how all of this comes together. And so, I was devastated. I completely shattered my confidence. So I went home. I called my mom. I'm like, I can't do this. I'm in the wrong place. I want to come home. This is not for me. And she says, you've only been gone for a week. Give it the rest of the month, and then we'll talk about it. And so for the next 3 weeks, I did the only thing that made any sense to me, and that was read papers. And there weren't that many research papers on FPGA and high-performance computing, but there were a lot of papers on high-performance computing in general. And so I read pretty much anything that I could find that was remotely related. And I found a lot of value there. And so much so that by the end of it, when the proposal was finally written, I had a lot of raw text just copy-pasted into that proposal. And that for me was sort of that confidence booster I needed to then get me through the PhD. And what I found value in was two different things. I found specific value in the research papers, which is when I read papers on FPGA and high performance computing, I found out what are people doing, what are the problems that exist, the very specific problems, and that people are trying to tackle. And then what I also found was potential future work that was very useful, because that's what makes up a chunk of the grant proposal. What are you going to do next? What are you going to improve on? So I learned all these specific practical information about what people were doing and what I was supposed to do as my PhD. Then I also found some general value. I found that there was a lot of practical knowledge to be gained. Even if I was reading papers on general high performance computing, I could find practical limitations of this approach. I could find an understanding and really draw that missing link between hardware and high performance computing and what I needed to do. And the second general value that I found was in the scientific process. Now, this wasn't really useful immediately in the proposal, but in future when I was writing papers, this helped me understand that how am I supposed to structure my ideas and my experiments, and what needs to happen for me to put together results and designs to form a paper and get that accepted. So I think I have a few minutes left, right? So I had 3 papers on my stack that I wanted to talk about in terms of the general value they're offering. There are 3 papers from OSDI, which is one of the high-tier operating system conferences. I don't think I have enough time to go through all, but I'll just really quickly go over the first one. It's just from a scheduling track, and all 3 papers are stuff that is outside my area of expertise. So this was for me a test as well to really apply that claim that there's general value to be had from these papers, even if I'm not an expert in them. So the paper that I will go over is the providing SLOs for resource harvesting VMs in cloud platforms. Now, this one, I did not know what SLOs are. I did not look up the definition either. I just wanted to test this out. And I did not know what resource harvesting VMs are. I just knew what a virtual machine is, and I knew what cloud platforms are. So the general discussion that happens for the field, let's look at that paragraph. And here they talk about that cloud providers rent resources to customers, and that when a virtual machine is deployed, it's going to consume a certain amount of resources. It makes perfect sense. That's what clouds are for. And of course, when you deploy a virtual machine, it's going to take a chunk of the physical server that it's running on. I think most people will agree with that statement. Then, customers can keep their virtual machines for seconds or years. Now, this I did not know. I knew you keep your virtual machine for some time, but I didn't know people were keeping it for years. But then also this point that, customers can request more VMs over time. I think that's what folks can generally agree on. When you have a product and if your demand goes up, you want more of that. So it happens. It happens in pretty much all facets of life. So then the next statement they make is that providers need to provide the illusion of perfectly elastic resources by reserving demand growth buffers while operating the infrastructure with high availability by transparently handling hardware failures. And this, again, makes sense. I mean, if you have a product and you know that sometimes people will want a lot more of it than they normally buy, then you want to have extra in stock. And knowing that some of that product may get spoiled, you want to have an even more capacity set aside just in case that happens, which is in the case of hardware failure. And then they make the claim that, for these reasons, it's important to leave unallocated capacity. So yeah, you want to have some inventory set aside in case you need more of what you're handing out to customers. The next paragraph sort of continues in that general basic overview information, and it says, it defines what spot VMs are, stuff that you can idle resources that you can hand over to folks with the understanding that they can be kicked out if somebody with a regular priority needs it. And this basically, what I want to point to here is the first sentence where it talks about SLOs. Now, we don't know what SLOs are, but looking at this sentence, I don't know what an SLO is, but looking at the sentence that to monetize this unallocated capacity, providers offer VMs with relaxed SLOs at discounted price. That is telling me that SLO has either some sort of constraint or a policy. So that's giving me enough context that if I come across this term again, or if I'm reading through this paper, I've got that back in the back of my mind that SLO, this abbreviation that I don't even know what it stands for, represents some form of a policy or a constraint. So the next statement is then that who will use this form of virtual machine is people who run batch jobs or workloads that can tolerate evictions and who would like that discounted price for the virtual machines. The next paragraph then talks about 4 problems that exist today with these types of evictable virtual machines. And then the last paragraph, before they get into an overview of the solution, they just put a statement that says, here's our solution. Dynamically, a new class of evictable VMs that is able to dynamically and flexibly harvest all the unallocated resources. And the key word here is harvest. Now, I didn't know what resource harvesting was. But when I read this sentence, I'm like, yeah, it's a basic evictable VM. It's a VM that's being spun up so that it can use the resources that are sitting idle. So now by just the first, fourth paragraph, I now understand the title completely. I'm not an expert in the field. I have no idea what SLO still stands for, but I am now getting a very good idea of what this paper is trying to do and what the field is trying to do. So I'm gonna skip this. I just want to point out that when I read through the background and related work, there was a bunch of other tidbits of information all over the place. For example, I found out that AWS is nice. They give you 2 minutes before they kick you out. Azure only gives you 30 seconds. So, but stuff like that was scattered all over this section 2. And then what I want to point out in this paper is also the scientific process, where if you look at the vertical axis here, the way that they structure the paper, and this was a really nice structure, I must say, where they looked at data and they used that data to set out, what they had to do and the constraints in which they had to do it. Then they defined their, new class of virtual machines. Then they talked about policies and how they were using machine learning to compute those policies or value those policies. Then they talked about integrating their new stuff into an existing scheduler, and then finally laid out the experiments and the analysis and the metrics that they were going to look at in order to demonstrate that they were successful in addressing the problems that they had identified way back in the first section. So for the next paper, I'm not going to go over this. The text is all there. If you're interested, you can go over it later. But I just want to point out that some of the papers at Usenix have these 3 logos up top, which is basically that the artifacts for this paper they are available, they have been evaluated, and have been reproduced. And basically what this is saying is that the source code of all the experiments being run in this paper is available for everyone to try out. And because of this, I would actually find this paper to be more credible than the one before it, because this means that I can confirm myself that everything that they are talking about this exists, and I can confirm for myself that the problem that they have talked about has been solved. And that's very useful. That's very important. So skipping right ahead to the end, I want to say, thank you for joining us for this session. And I would want to welcome you to the next session, which is going to be in the next RIG meeting, and where we're going to look at identifying worthwhile papers, going through papers, skimming through them and looking for flags that tell us whether this paper is worth spending a couple of hours reading, or maybe we should be looking for another paper. If you have comments, suggestions, feedback, there was a very nice comment. I didn't get a chance to acknowledge it, yes, but I will stop using motherhood apple pie. I don't think that's appropriate. So thank you for pointing that out. And so if you're interested in joining the paper reading group as well, we have QR code there and the link to the form. So please do that. And with that, thank you everyone again. And if you have, if you have time and if you have any comments or suggestions or feedback, the floor is yours. Thank you.
So I'll ask the first question. You were talking about people reviewing papers, and I was wondering if you could share how many people review different kinds of papers, and when somebody submits a paper, what are they up against as far as the number and type of reviewers that typically go over it?
So normally there are 3 to 4 reviewers. So what happens is for conferences, usually there's 2 deadlines. One's for the abstract, where the authors are supposed to just submit that summary of their paper, and then the submission website sort of then invites reviewers to come in and select which papers they want to review after declaring conflicts of interest, of course. And then once the final submissions are in, then 3 to 4 reviewers are assigned to each paper based on the preferences that they had listed before. In case of a tie, sometimes an extra reviewer is also brought in. If some reviewers feel this is good, some feel that's not so much, then an extra reviewer could be brought in to sort of give that final or break that tie. For journals, what happens is that the editor receives the paper, and then the editor then reaches out to potential reviewers who have expertise in the field and asks them, are you interested in reviewing this? And again, then the number of reviewers will depend on the exact journal and what the tier of that journal it is.
We have a request that you put the QR code back up. I think Ahmed would also be interested in hearing what people were looking for in a talk about how to read papers, since we have 2 other talks, and whether this was hitting the right level or whether you were looking for something more or less involved, or from the point of view of a general interest, or somebody who might write a paper. If we had any feedback like that, it would be great to get, or questions.
I don't want to speak on the behalf of everyone, but I'll definitely say that it was very demystifying in a great way. I thought all the points were really clear, and at a high level, I have a much better understanding of what it takes to write a good research paper. So yeah, I think you really hit the mark for me. So thanks.
Good. Oh, and Zio Leo, thank you for posting the link there too, for those who don't have phones. So we're going to post these slides on the research.redhat.com site, and I apologize that we didn't do that in advance. I forgot that we were going to run into this problem with the Google restriction. So we'll get that information out so you can go through in detail the stuff that wasn't presented verbally in the meeting. Okay. Thank you, Ahmed.
Thank you.
I maybe have one question if you.
Oh, sure. Go ahead. Go ahead.
I'd love to hear your thoughts on maybe you mentioned, you know, these long-standing conferences, they're more and more difficult. I guess it's sort of a double-edged sword where you have this elitism, I guess, maybe in a way that maybe there's like narrow-mindedness, or maybe only very specific, I guess, perspectives make it into these conferences, if that makes sense. Like questioning the status quo maybe isn't as accepted in those conferences. Would you say like a response to that is just have more conferences and, you know, go and submit to other conferences, or do you think there are other things that can be done to solve that particular issue, if you even think it's an issue?
That's a tricky problem. I agree that there's a lot of conferences, and there's a lot of, you know, program chairs, and there's a lot of papers that get submitted, and there's a lot of biases that exist. But that being said, I think that there's a lot of forums out there. So and to be honest, if a paper has sufficient quality, if it doesn't get accepted at one prestigious place, it can get accepted in another. But of course, that doesn't mean that it is guaranteed in any prestigious place at all. So that is why we have the next session, and that's the whole point there. That there are cases, because of the human factor involved, where sometimes you have these extraordinary pieces of work that just can't make it into any high-tier conference, and they end up appearing in a place where people don't consider to be that high-tiered. And that's why recognition for a paper should not be purely on the basis of conference. Just because this paper was published at, you know, XYZ conference doesn't automatically make it a great paper. We have to, you know, be able to pick out the flags that exist in that paper and the indicators that show that whether that work done was actual proper work, or whether that's just fancy wording and few results that have been extrapolated. So I guess, see, tiering, in my opinion, that's the most I can offer. My opinion, tiering is a perception. You can create any metric to make anything look as good as you want. And so in my opinion, that's the point of these paper reading groups, where we have papers that we're discussing from across the board, not just from a limited set of conferences, and we have multiple people reading multiple papers from different places, then we're able to really find the really, you know, the hidden gems out there, as well as the more established ones.
Awesome, thanks.
Okay, thank you, Ahmed. That was great.
Can I have a question?
Oh, yes, certainly, Máirín. Sorry. Go ahead.
Yeah. So I was just talking about the papers with the source code, provided source code. So basically, in my courses, I have read few papers about some implementations on some simulators or something like that. those papers were basically, we needed to write some dummy papers, but those papers just basically meant they have implemented something and they have done it on simulator. So the problem there was the implementations were not very clear, or were not easy to use, or basically the source code does not have all the things sorted out. There were a lot of bugs that we need to first get cleared, or basically removed from the code and then run it. And after running it, we also saw there were multiple defects in the implementations as well. So is it always a good thing that the source code is present, so we should blindly follow it, or are there any pin, you can say anything we can do, or we can check beforehand, so that we don't fall into the trap like I fall into?
So there's this increasing trend of not having a very strict review process where it's either an accept or a reject. And if there are minor discrepancies or small things, then giving the authors a chance to address them and then resubmit. My opinion is that code should always be open. Just because if we cannot test or verify or reproduce the results, then we're just taking things at face value. Code should always be open, but it should not be such a strict process that if there are minor mistakes, then it's just thrown aside. The authors, there should be feedback from the reviewers to the authors. The authors should have a chance of fixing that. I mean, we patch software all the time. We update software all the time. Shouldn't be any different for the stuff we're doing in research papers. But code should be open so that it can be reproduced and verified and then used by folks to build new things on top of it.
Thanks.
Okay. So if you have any more questions or comments, feel free to contact us directly. And like I said, we'll try to get the slides out to people who weren't able to access them. I think the next slides probably are more accessible. At least I'll put the link up. And the next presentation is from Cagri Yoruk on the ChRIS project and the MOC integration.
Okay, let me share my screen. Can you guys see my screen?
Not yet.
Is it loading?
Ah, now it's loading. Yep.
Okay.
It's good.
Okay. Okay, hello everyone. My name is Cagri Yoruk, and I'll be presenting my work over my internship period at Red Hat today, which is ChRIS MOC integration. This is a little bit of overview of our agenda today. I'm going to be introducing myself and the ChRIS project and the work I've done before joining Red Hat, and my current work and the impact of it. And then I'll wrap it up with some closing notes. As I said, my name is Cagri Yoruk, and I'm currently a graduate student at Boston University studying electrical and computer engineering, and I'm going to be graduating this May. I started Red Hat approximately 2 months ago as in the ChRIS team as a backend developer. Yes. The ChRIS project. So what is ChRIS? ChRIS essentially is an open source platform that utilizes cloud technologies to make medical application development accessible by everyone. And why do we use ChRIS? Because ChRIS allows researchers the ability to run their applications in a public cloud to drive medical innovation. And ChRIS started as a project at Boston Children's Hospital to do 3D visualization and do collaboration around medical imaging between researchers. And I believe there are three main reasons why do we use ChRIS. And because the more people use ChRIS, there's going to be more data. And thanks to the Mass Open Cloud Initiative, we're having access to more compute power. And of course, with ChRIS, we have more collaboration. I believe there are two quotes that indicates ChRIS motives greatly, and this was given by one of my mentors, Rudolf Pienaar, at Red Hat Summit in 2018. And the first one is, there's about 2 decades worth of amazing tools that exist in the research community, but these almost never make it out of the clinical front lines. And this indicates that there are really great advancements in technology and great research. However, somehow these research cannot make it to the hospitals and cannot make it to the clinical front lines. And it's because no clinician is ever going to fire up a Linux terminal, type in some commands, think about SSH and SCP, and log into a cluster. And from this quote, we can see that like majority of the clinicians don't have this technological background to do advanced like machine learning algorithms, type some commands, write some scripts, and etc. So I believe these two quotes really indicate the ChRIS motives. And because of these problems, ChRIS gives a great UI and really user-friendly, I guess we can say. And people or clinicians can upload their data, run like machine learning algorithms, classifications by selecting like the plugins. So I think, yeah, this is an example of the UI. So I'll be going over the architecture now. I'll be going over the architecture because it is closely related to my work in the ChRIS team. In the top, we have the ChRIS backend lying in Boston Children's Hospital. And below that, we have our services, the input-output handler and the process manager. And down here, we have the Swift storage. This Swift storage lives in OpenStack, and this is basically where we store our files and directories. And if I have to give an example of the operations, what we do is if we want to push some files to this Swift storage, we basically call this input-output handler, and then it directly pushes files to the Swift storage. Whenever we want to run an application or a plugin, let's say we run it through the process manager. And what the process manager does is it initiates the process first and takes all the data we have specified from the Swift storage. And then on top of that, it runs the plugins that we specified. And after that, it publishes the output back to the Swift storage. And of course, again, we can pull these output files from the Swift storage back to our local data with this input-output handler. That was it for the ChRIS project, and now I'm going to be talking about the work I've done before joining Red Hat. In fall 2020, I was working in a student group for a project called Containerizing Neural Networks for Medical Compute. And our goal was to develop a ChRIS plugin that provides a text report of brain MRI images using convolutional neural networks for clinical users at Boston Children's Hospital. And there's a picture of our inference pipeline that we built. And it basically takes medical standard DICOM files as input. And then we convert them to PNG files and feed them to our MRI CNN, which is the convolutional neural network. And after that, after we get our prediction, we convert them to NumPy images, and then we feed them to another plugin called MGZ to load report. And this basically spits out a segmented brain report as a PDF file. And another one of our goals was to build this, run this plugin or inference on Mass Open Cloud. And to do that, we encountered a couple of problems. This project was built in 5 sprints, and it took us nearly 4 sprints before we run any deploy any services or run any applications or plugins on Mass Open Cloud. And the first one is, even though we had a documentation, we can say that it was not sufficient. So we had a lack of documentation on the ChRIS regarding the MOC integration. And even though after having this integration, after deploying our services, sometimes we didn't have any persistent volume available in the cluster. Sometimes the routes were not available, and sometimes there was a maintenance. So all of these problems we encountered gave rise to building a MOC integration document that can be treated as a ground truth, and start working on a local OpenShift cluster. And after that, we come to my work in ChRIS. So in ChRIS team, I work on testing, debugging ChRIS services on the local and the MOC OpenShift, help building new ChRIS services, and also building this documentation with the experience I have over a couple months. This is the GitHub repo, the introduction of the documentation I built as MOC integration. I don't think it's like we cannot understand the scope of this documentation with this slide, so I'm going to show it over here a little bit, go over it really quickly. So we can see that we have a couple steps integrating ChRIS with the MOC. It's like registering to Mass Open Cloud, adding projects. And I built this documentation on top of the documentation we already had. So I try to give as much detail as I can. Installing the OpenShift CLI tool, which is the command line interface tool. Creating secrets for the project, deploying our services. And it's loading. Deploying the process manager, running our plugins on the OpenShift environment, how to install it, downloading our scripts. And as an additional step, I also show how to build a local OpenShift cluster for the ChRIS and how to deploy our services again. So I think building this local OpenShift cluster was really great, expediting the process of debugging or testing some services. So yeah. Another thing was, as I said, debugging. And I don't think I'd have enough time to go over this bug, but if you want to check it out, the exact process that I did, you can go over to the source over here that I specified. This is basically a status blog that I wrote. I write my experience in Red Hat and the work I do. So yes. Next, I have the impact of the work. So as I said, I was in a student team last semester, and it took us a great amount of time to run these applications and deploying our services on Mass Open Cloud. And with this documentation, I immediately saw the feedback from the Northeastern University student team that we have this semester, and their onboarding process was much faster compared to my experience. And also, I was able to continue develop and test applications with building this local OpenShift cluster. And I'm going to wrap this presentation up with a couple comments. Recently, 3-4 weeks ago, we had major changes happen to the ChRIS ancillary services. So we need to integrate them with MOC to work again. And my job is or what I want to do is help building this services to work with MOC and revise this MOC integration document until the end of my internship. And thank you for listening to me. I'm open to any questions if you have.
Cagri, how did you get interested in ChRIS in the first place?
So it was, so this project was that I talked about was containerizing neural networks. It was a class project for one of my classes, cloud computing in BU. And there were a couple, I guess, descriptions and topics about the projects. And the moment I saw ChRIS and the impact of it, I was, I guess, really interested. And before I select this project, I watch all the series of ChRIS, like how was it built, like the cloud computing aspect of it. So all of those, I guess, did a little bit of impact.
I really like the fact that you kept a blog. That's unusual, but I would have been following it if I'd known. I'm going to catch up on it now.
Yeah, Mo wanted me to create it a couple weeks ago, and I think it's really great to do this kind of stuff.
Yeah, especially to help other people who are going to work on the project or other students, like Ahmed was saying when he first started working on his project and felt completely overwhelmed for a while. It's nice to be able to look at somebody else's blog and say, oh, wait, I'm not the only one.
Yeah, definitely.
So do you think you're going to go on and continue working in this field?
In this field, you mean like cloud computing or like in ChRIS in general?
The intersection of health and cloud computing, yeah.
I'm not sure about health, but I definitely want to continue work on cloud computing.
Cool. So if there are other students listening, there are other opportunities to work on projects, either through classes or through open source software. And they are welcome to get in touch with us or get in touch with you afterwards if they want more.
Of course, yeah. I think I have my status blog and my communication is probably there. So yeah, they can reach me out here or Slack channel. Yeah.
Awesome. Thank you so much, Cagri.
Yeah, thanks for having me.
I just wanted to ask Cagri one thing before we wrapped up the presentation, if you don't mind.
Of course.
Yeah, sure.
I'm an undergraduate student. I'm in my third year, and I was interested in getting into cloud computing. So the main question I wanted to ask is, how did you get into it, and what would you recommend for someone who's just starting out?
Yeah, so before I joined this project, I actually didn't have any experience in cloud computing, but I believe that one of the most important tools is learning about either Docker or our version's Podman, container tools. I believe container tools are really important in cloud computing, so I guess you can get started with those.
All right, thanks. I'll check it out.
Yep, no problem.
Any other questions or comments? Oh, we have one in the chat from Salvador Cartagena. I hope I pronounced that right. How did you come up with this project, Cagri?
Let me see. Okay. The chat.
Yeah, the last question
yeah.
is, how did you come up with this project?
Okay, I guess it's about the MOC integration. So as I said, it was my experience from last semester that I wasn't able to get on board in ChRIS really fast. So I guess this gave an impact, or after last semester, I can say I was really interested to continue to work on ChRIS. And when I reached out my mentors, I wanted to work on this project. Along the way, they gave me this job, I guess, creating a document or working on this MOC integration. So yes, I guess it just happened along the way.
Yeah, the mechanics of it is we have Red Hat internships that happen during the school year or during the summer. And then we also have the collaboratory at BU, which for BU and Northeastern students gives people an opportunity to work on campus directly through the collaboratory too. So depending on where you are in the world, those are the choices as far as getting, really, really involved with a Red Hat person. The other option, of course, is just contributing as an open source software developer and looking for good projects related to that. I'd recommend looking at the Massachusetts Open Cloud website as well. There's a lot of project information on there, and there have been a lot of presentations from different people who've been working on clouds there. And everyone is very open and friendly and happy to respond if you just send an email saying, I'm interested in your project, what could I do? A lot of times they'll have suggestions for things you can start up on. Okay, if that's all the questions, thank you very much, Cagri, for presenting. That was really interesting. Thanks to your mentors too. I know Mo was here and posted the link to the blog, and she's a long-term ChRIS contributor. So
yeah, thanks for having me.